In the last video, I introduced 4 properties of measures that I would like to prove now. I ran out of time in the last video, and I'd like to go ahead and give the proofs. So first of all, let's talk about monotonicity. The theorem that says that if E is a subset of F, then the measure of E is less than or equal to the measure of F. It certainly seems intuitively obvious that a smaller thing should not have a bigger measure than a bigger thing, right? So let me just go ahead and outline a sketch of a proof that says, okay, so proof 1. Let E be a subset of F, then the measure of F is equal to, that's not a very good F, let me start on a new line and try that again. Then the measure of F, so mu of F is equal to the measure of E plus the measure of F take away E. So by the property of sigma algebras that we showed in the last video, this is a measurable set, and this is also a measurable set, of course. So by the property of measures that says that measures are additive, this equation is true. But this thing right here is non-negative, so is greater than or equal to just the measure of E. If we take this away, we're taking away something that is either positive or zero. If it's positive, it's strict inequality. If it's zero, then it's equality. So that's all we need to do for property 1. Again, very straightforward. Sigma subadditivity. Now this one's a little bit more involved. What we have to do is, and we'll do something similar for sigma subadditivity to what we'll do for continuity from below. But let me go ahead and try it with sigma subadditivity first. What we're going to do is we're going to say that these sets, that there are a bunch of sets that are not necessarily disjoint. So we have E sub 1, E sub 2, E sub 3, and so on. Well, what we're going to need to do is define a new family of sets. And this new family of sets will be E prime sub k, as k goes from 1 to infinity. Let E prime of 1, or E prime sub 1, just be equal to E sub 1. Okay, no difference there. Now for k is greater than or equal to 2, let E prime sub k be equal to E sub k minus the union from k equals 1 to infinity of E, sorry, not to infinity. The union from k equals 1, union, I shouldn't use k again. The union from n equals 1 to k minus 1 of E sub n. Alright, so what have we done here? Well, we have a set that ek prime is going to be everything that is in E sub k, but it's not in the union of all the E sub n's that come before E sub k. So it's in E sub k, but it's not in anything that comes before it. And so it's clear that all of the E sub k primes are disjoint. Okay? All the E sub k primes and I'm using both a prime and an apostrophe, which looks weird, but whatever, are pairwise disjoint. Okay, because if E sub j is less than E sub k, then if E sub j prime is less than E sub k prime, then E sub k prime doesn't have anything that in the union of all the things that came before it. In particular, it doesn't have anything from E sub j, which means it doesn't have anything from E sub j prime. Okay, so they're pairwise disjoint, but the union from k equals 1 to infinity of E sub k prime is equal to the union from k equals 1 to infinity of E sub k. And the reason that's true is that if an element is in E sub k, well, first of all, one direction clearly holds, right? This is a subset of that, because everything, if you're in E sub k prime, you're definitely in E sub k, okay? But if you're in this union of E sub k, then there's some first k such that you're in E sub k, right? You might be in lots of different E sub k, but there's definitely a first one, just by the well-ordering property of the natural numbers. And so take that first one. Well, you're not in any of the ones before it, so you'll be in, if you're in E sub j, and that's the first one, then you're definitely in E sub j prime as well. So you're going to be in, if you're in one of the E sub k's, you're in one of the E sub k primes as well. And so these two sets are equal. Now the measure, so the measure of the union from k equals 1 to infinity of E sub k is equal to the measure of the union from k equals 1 to infinity of E sub k prime, because it's exactly the same set. But this, since these are all disjoint, is going to be the sum from k equals 1 to infinity of E sub k, of the measure of E sub k prime. I probably shouldn't put my mu inside that sigma. Sigma wants a space. Alright, measure of E sub k prime. But then this right here is going to be less than or equal to, since each E sub k prime is a subset of E sub k, the sum from k equals 1 to infinity of mu of E sub k. Kind of a nice proof. Anyway, this gives me the relation I want. If I just circle this part right here, that's what I really want. I've used my E sub k primes, but I don't need them anymore. This is the thing that I'm really after. Okay, so that's given us our first property, monotonicity, and it's also given us sigma subadditivity. Now, as far as continuity from below goes, let's assume these are our sets, and we can imagine that we keep going infinitely outward, more and more and more of them. But we're going to do something similar. We're going to take E sub 1, or E sub 1 prime, and it's going to be that set right there. And then E sub 2 prime is going to be everything that's in E sub 2 but not in E sub 1. And E sub 3 prime, likewise, is going to be everything that's in E sub 3 but not in E sub 2. And we keep going out like this. So we're going to have these sets that are all disjoint, and they no longer contain each other, of course, because they're disjoint. But their union is still going to be the same as the original union. Okay, that's the basic idea behind the proof. Now, but first, we need to take care of the infinite case, because I'm assuming here that they're all finite. But 3. Okay, so if one of the E sub k, well, let me just remind you what we're trying to prove here. We're trying to prove that if we have E sub 1 contained in E sub 2, contained in E sub 3, and so on, then the measure of their unions is the limit of their measures. So their union is really just the limit, could be thought of the limit of all of these sets, right? As we get bigger and bigger, we're getting closer and closer to some set that is the union of all of them. And we show that the limit of the measures is the measure of the limits, if you will. Okay, so if one of the E sub k's has measure infinity, then the union k equals 1 to infinity of E sub k has measure infinity by monotonicity. That's the property we just proved, right? Since E sub k is a subset of this, monotonicity tells us that this has to have a measure at least as big, and since there's nothing bigger than infinity, that means it has to have measure infinity. Alright, but then also, for all n greater than or equal to k, for all n greater than or equal to k, E sub n has measure infinity as well, because E sub n contains E sub k. So E sub n has measure infinity. And then we get the union, or the measure of the union from k equals 1 to infinity of E sub k is just equal to infinity but that's also equal to the limit as n goes to infinity of infinity, which is just the measure of e sub n. Alright, and so there we have, if we're infinite, then that's how this theorem follows. Now, assume all e sub k finite. Alright then. Well, what we can do is we can go ahead and take the sum of all of these, the measures of these new e sub k prime. Let me go ahead and do that. For all k, define e sub k prime to be just e sub k minus e sub k minus 1. And here I don't have to take the union of all of the other e sub k's, because I know that they're all contained in e sub k, and they're all contained in e sub k minus 1. So if I take away e sub k minus 1, I'm taking away everything that came before e sub k. Alright, so define e sub k prime this way, then all the e sub k primes are pairwise disjoint. And so the union from k equals 1 to infinity of e sub k, the measure of that right there, is equal to the union, the measure of the union from k equals 1 to infinity of e sub k prime, just because, again, this union is the same as that union there, so their measures are the same. But this right here is the sum from k equals 1 to infinity of the measure of e sub k prime, but this here is equal to the to the limit as k goes to infinity, or sorry, as n goes to infinity, of the sum. Whoops, that's supposed to be a signal. Alright, the limit as n goes to infinity of the sum from k equals 1 to n of e sub k prime. But then the sum from k equals 1 to n of e sub k prime, whoa, what happened there? Just zoomed in, didn't mean to do that. The sum of all these e sub k prime is just going to be equal to the, measure of e sub k, hold on. Okay, I see what the problem was. I was supposed to write the sum not of e sub k's, but of the measure of the e sub k primes. So let me go ahead and do that. Let me just move this a little bit over to the right, because I can. While I'm at it, I can make my k look a little bit nicer. Mu of e sub k prime is the sum from k equals 1 to infinity of the mu, of the measure of e sub k minus, or slash, e sub k minus 1. Now, there's something special about sets that are subsets of each other. If I have two sets that are subsets of each other, then the measure of one set minus the other is just going to be the measure of one set minus the measure of the other. And what I mean by that is, in general, if I have two sets that are not subsets of each other, and I take the measure of, let's say, this whole set A minus this whole set B, I'm taking all of A except for this little bit of B. And so, of course, it wouldn't make sense for me to take all of the measure of A and subtract all of the measure of B, because for all I know, B could be even a bigger set than A, and I definitely don't want to subtract a bigger thing from a smaller thing. But if A is a set and B is entirely contained in A, well then, the measure of A minus B is just going to be the measure of A minus the measure of B, because I'm just subtracting the measure of this part right here. and that's easy to show just by the definitions and properties that we've already proven. So I can replace this measure of e sub k minus e sub k minus 1 with the sum, with the sum from k equals 1 to, oh, and this wasn't supposed to be infinity, this was supposed to be n. I had already, I had taken the limit of that thing, right? So the limit, we're taking the limit as n goes to infinity of the sum from k equals 1 to n of the measure of e sub k minus the measure of e sub k minus 1. But then this here is a telescoping series. We get the measure of e sub 1 minus the measure, and we'll define e sub 0 equals the empty set, just so that this conventionally works. Okay, so then we have the measure of e sub k minus 1 is 0, and so we have the measure of e sub 1, but then we have the measure of e sub 2 minus the measure of e sub 1, and then the measure of e sub 3 minus the measure of e sub 2, and so on until we just get the measure of e sub n. So this thing right here is going to be the limit as n goes to infinity of the measure of e sub n. This series telescopes very nicely and just gives us one term that we have to worry about. So these two series are actually equal to each other. And so the limits are equal to each other. And that right there is what we wanted to prove. We wanted to prove, now let me go all the way back to where I was before. We wanted to prove that the measure of the union of all of these e sub k is equal to, and there are no inequalities here, everything was strict equality if you look along what we just did, is equal to the limit as n approaches infinity of the measure of e sub n. So that's how we do that. All we did was we took these sets and we took the complements, or we subtracted these sets from each other to get a bunch of disjoint ones, and their union turns out to be this nice sum, or the measure of their union is this nice sum, but it's just the limit of each one if we keep going like that. Alright, property number 4, continuity from above. We're actually going to use continuity from below to prove this. But let's assume that e sub 1 has a finite measure. Then we don't have to deal with an infinite case, which is kind of nice. We can just deal with the finite case. So now for this part of the theorem, we're assuming that instead of these sets getting bigger and bigger, they're getting smaller and smaller. So the next set after this red one might look something like, oh, I don't know, let me get a different shape than this. Maybe it'll look something like this. Maybe we can fill that up. And then maybe there's another set inside there that looks something like, I don't know, something like that. We can go ahead and fill that up. And they keep getting smaller and smaller. So instead of saying that they get bigger and bigger, this is supposed to be a kind of an ellipsis, dot 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 thing going on there. And so instead of getting bigger, they get smaller. So that ellipsis would properly belong in here. They get smaller, and then there's an infinite number of them. But their intersection might end up being, well, hopefully non-empty. Not necessarily, because we're not assuming they're closed. But their intersection might actually have positive measure, for all we know. Well, how can we prove that the measure of the intersection is the limit of the measures? Certainly their measures are getting smaller and smaller, but all we need to do really is use the property that we just proved, except this time, let's go ahead and let this equal e sub 1 right here, this outer one. Maybe I should use a different color here, e sub 1. But for each k, we're going to define, let me use a brand new color here, I'll use this orange. So define f sub k, where f sub k equals, let's see, e sub 1 minus e sub k. Alright, and so here's e sub 2, here's e sub 3, and they're going down, right, e sub 4. And so these sets are getting smaller and smaller. So if I take f sub 1, well, that's just going to be the empty set, right? E sub 1 minus e sub 1, the empty set. E sub 2 is going to be f sub 2, sorry, is going to be this kind of dark blue-gray region. And then f sub 2 will be E sub 1 minus the green region, right? So we'll have the blue, both the blue-gray and the lighter blue here, and that'll be our f sub 2, or our f sub 3 actually. And then our f sub 4 will be everything except the red region, so they're getting bigger and bigger and bigger. Our f sub 5 is everything except this pentagon shape and what's inside it, and so on. Okay, so we have these bigger and bigger and bigger sets, and they converge by our previous theorem, so we can go ahead and use that. I'm not going to actually write that down because we're running out of time, but I think you get the idea how that works. And we're assuming that everything is finite here, so we can subtract things, and it's fairly easy to construct the proof from there just based on what I've said. So that's the proof of our 4 basic properties. I'll talk about one more property called the Borel-Cantelli lemma in the next video. Thanks for watching.